Hello friends, I would like to welcome everyone to our monthly webinar series. So in this webinar, I have the honor of welcoming Dr. Heinz Kabutz to speak in our webinar. So Dr. Heinz is a very popular personality. He speaks in so many conferences and he is, the Java util concurrency, there is a parallel programming is very tricky to do. And finding bugs is probably the oddest thing. But Dr. Heinz specializes in that. So in this session, he's going to share us some best practices on how to troubleshoot and get to the root cause of these tricky problems. So with that, I'm handing over to Heinz. Heinz, it's absolutely an honor to have you come and speak in our forum. Thank you very much, Heinz.
And Ram, thanks so much for inviting me. It's an absolute honor and pleasure to do this. There was no hesitation when you said, would you like this? Like, oh yeah, I'd love to talk to your crowd. It's going to be a lot of fun.
Yeah.
So let me turn on my screen sharing and then we'll begin. Mm-hmm. So I'm going to go to live sharing. All right. So this is going to be a little bit different. I'm a bit different when it comes to the way that I do things, and the way that I'm going to do it, you can see sort of on my up here above me that you can see these are the questions, right? So what we'll do is I don't want you to wait until the end of the talk and then bring your questions, because what will happen is, on slide 13, I'll show you something and you'll go like, that doesn't look right. I'm sure I just made a mistake there. And you'll want to ask me a question, but then you have to wait until right at the end to ask me the question, by which time you've already lost interest. Maybe you've already gone and you're doing something else. So you are welcome to interrupt me anytime by sending your question to the chat, and then the team will send it to me on this link, and then we can zoom into that and look at the question together. Right, so this is how we'll do it. It's a bit different to other webinars, but I like to have the webinars to be very interactive. I don't want to be talking just to a mirror. I'd rather be talking to an audience, and this is how we can keep it interesting and fun for you as well. So just remember, ask questions in the chat, and they'll copy it over for me so that I can see it. All right, so let's get going, and we're going to start right at the beginning, from bugs to brilliance, master java.util concurrent, and I want to start with a class that you no doubt have seen before. This is java.util vector, and vector's been around since Java 1.0, and it was designed from the beginning to be thread safe. But at the time when they designed it, the reasoning about threading wasn't that well developed. And they didn't have a rule book as to how multiple threads should cooperate looking at shared data. And the thing we worry about here is shared mutable data. If you've got shared data that's not mutable, that's fine. But if it's mutable data that can change, then shared is a problem between multiple threads, because we might not see each other's updates. And so most of the methods are synchronized, and they're locking on themselves, in other words, on the object itself, but they missed a few synchronization points, and this can actually cause some issues. For example, here's the first version of Vector 1.0, and they had the element count protected. Now, that already poses a problem, because you could subclass Vector, and you could update element count from outside the synchronized, and then it would not be thread safe. So that's already a danger. It's not a very safe class. And what they did was they have the add element method synchronized, meaning that you can only one thread at a time can call add element on a particular vector instance, because synchronize is like locking on this. But they did not synchronize size. And the reasoning was, size, all we're doing is returning element count. We can't have a race condition. But they missed the point that you might have stale values. So if you have multiple threads, and one thread is updating vector, and the other thread is reading size, they might see stale values, out-of-date values that are no longer correct. So here's another version 1.1, and in version 1.1, they actually went and they introduced a potential race condition, which is really weird, because how do you get a race condition from this? And all they really did, I mean, they did some other things as well, but the main thing here is they said implements java.io serializable. So how does serializable introduce a race condition? Well, what happened now is that you could potentially change a vector at the same time as some other thread is busy serializing the vector. So again, you could get corruption and problems. So I just want to quickly do something because I see that the video is not as good as I would like it to be. So quick in-flight adjustment and see if it makes a difference. If I can find my mouse. Where's my mouse? My mouse has disappeared. Okay, let's try doing something else, which is, see if that's different. That's better. Then if you notice, it's slightly darker now. Before it was a bit washed out. And I spent so much money on this equipment that I'm using. I want it to be as good as possible. All right. So let's continue. So that was Java 1.1. They introduced this race condition, and they actually fixed that in Java 1.4. So 1.4, they fixed both the race condition and the visibility on the size by, first of all, making size synchronized. That was the first thing, so that you always read up-to-date values. And secondly, they introduced the write object method, which was synchronized so that you couldn't change the vector at the same time as you were writing it. So that's great. So everything's fantastic up to now. However, this happens quite often. When they added the synchronized write object, they also introduced a potential deadlock into the vector. Now this is very obscure, and basically what we're saying is that if you have two different vectors, and vector 1 points to vector 2, in other words, it contains vector 2, contains a reference to vector 2, and vector 2 contains a reference back to vector 1, and you have two threads, and each thread is writing one of the two vectors at the same time, you could get a deadlock, right? This is like extremely obscure situation. And you might say, well, that's never going to happen. Well, probably not. And that's what I said in my newsletter. I said this is, and if you're not on my newsletter, you really owe it to yourself to sign up. Go to www.javaspecialist.eu and you can get them all there. Sign up so you don't miss any. And anyway, so it's 184. Have a look at that. I said this will never happen. It's extremely unlikely this will ever happen. But somebody actually found this situation at IBM, and they coded a specific workaround in IBM to solve this problem. Sorry, one second. All right. So in Java 1.7, one of the people from IBM went and added this code to the vector. So they specifically move the synchronize away from the method and move it into the method, and they call clone they call clone instead of write fields in order to make a copy of the whole array and then serialize that later on. So this had the effect that we didn't write at the same time whilst holding the lock. And because of that, if we did have two vectors, one pointing to the other and pointing back, we would clone the arrays and we would write the clones, and this would no longer cause a deadlock. So this is fantastic. A bit more work to make a clone, but other than that, at least we didn't have potential deadlocks. So basically, Vector 1.7 seemed to be okay. I'm not sure if there are bugs, there probably are, but I'm not sure which ones they are. But then they added Java 8, they added the for each method. And for each took a consumer, and consumer is some foreign implementation of an action. And they would then call the action.accept whilst holding the lock, whilst being synchronized. And this again, you can see it in the middle here, action.accept. This again introduced a potential deadlock, because if you have two vectors and two threads, and inside the for each, the action refers to the other vector, for example, call size or something like that, it potentially again can deadlock. Again, a bit obscure, and it's something which I have considered logging a bug against it, but I don't really have a good solution on how to fix it. And this is sort of the principle I use is, if I can't think of a good explanation or good solution, I'm not going to log a bug. And I've had this a few times where I was going to log a bug for something, and I didn't have and I tried to write a fix. I couldn't come up with a good fix, and then I stopped. I stopped writing a bug, because if I can't think of, often my bugs are wrong. In other words, it's my misunderstanding of the situation that makes me want to log a bug. So 99% of the time, when I think it's a bug, it's actually a bug in my own code, not in the JDK. But sometimes it is a bug in the JDK, but it's very rare, not very often. All right. So the takeaway is that thread safety is quite subtle, and there are lots of tests for vector. But these tests don't always expose the concurrency bugs. We actually need to know precisely what to look for. Are we looking for deadlocks? Are we looking for race conditions, visibility? And we need to test for those specific things. We can't just say, well, show me all bugs. And there have been attempts to write systems like that. I've not seen anyone that really works that well. They sometimes work, but they don't work that well. All right, so I've sort of shown you a simple class that we all know, vector, and I've shown you that even it's a simple class, we all know it, even that has challenges to get that right, to get the concurrency right. And so what I want to look at here is sort of the idea of doing a teardown of java.util concurrent. And I started recording a bunch of courses on java.util concurrent to have like the definitive guide to java.util concurrent that no one will ever watch. That's basically the idea. It's a bit like the art of computer programming. You know, I'm sure you've read that by now. You hope you've read it by now. The Art of Computer Programming. It's this massive volume of books by who wrote that now? Donald Knuth, I think, wrote that. Is that right? I think he wrote The Art of Computer Programming. So you should have a copy. You know, have a copy on a bookshelf and read it. But like that, I wanted to have something like that, but for java.util concurrent. So I started looking at, for example, array blocking queue, and then copy and write collections. And then I went to the link blocking queue and the link blocking deck. And now I'm working on the next one, which will be lock support and some other things as well. And the idea is this, that in order to see, or in order to understand how we should write concurrent code, it's helpful to study how the authors of Java have written their concurrent utilities. And so that's why I've been like working through it line by line in incredible detail, more for myself than as a course. And just to give you an idea of how detailed this is, array blocking queue has 4 hours of walkthrough, 4 hours of instruction. The copy and write collection is also 4 hours. Link blocking queue and deck about 5 hours. So it's extremely detailed. But it's no one's done anything even close to this. That's for sure. But from this, I've discovered lots of things. First of all, we all know that the Java memory model is our rule book for how threads interact with one another in terms of memory, and happens before ordering, access safety, etc. The problem is that we can't take our class and give it to somebody to test whether or not our class adheres to the Java memory model 100%. We just have to run it and hope it works, right? and some bugs are very, very hard to detect. Now, I live on an island. And I was chatting to somebody on last Friday, and he said to me, "Yeah, I can imagine. Yeah, you probably in the morning, every day you're on the beach having cocktails, you know, and but that's probably not true." And I said, "Well, it's not that far from the truth. Every day I'm on the beach going for a run, doing my push-ups, every single day. When I'm in Crete." I then have cocktails, not in the morning. I've got things to do, but I certainly enjoy myself here on the beach. But one thing which is interesting is the driving, right? The driving, because people drive here as if there is no tomorrow. They're very chilled and relaxed, except when they get behind the steering wheel of a car. Then they drive like lunatics. And I don't know where you're from, but you might have similar experiences where you're from. But so what I'm saying is that the driving is interesting, and recently they've cracked down on traffic violations. In the past, you could do almost anything and no one cared. I remember one time I was driving somewhere, and maybe I shouldn't say this publicly, but let's just say that I did something I probably shouldn't have done, or I definitely shouldn't have done, and there was a cop car coming up the road towards me. They didn't care. They just they just let me do whatever I want to do, But it's different now. Now it's different. Since the beginning of the year, they've been cracking down. And a lot of the rules, we don't even know the rules, It's like one rule that I heard recently is you can't take your shopping and put it on your back seat. You get this massive fine, like €250 fine, if they catch you. And they'll probably take away your license for a week or something, or a month. They're like, why? Why can't you do that? No, you got to put it in the boot of the car, in the trunk, the back. You can't put it on the back seat, because what if you have an accident that's going to fly forward? That's true, but if you see how people drive here, you'll wonder why you have these rules. And the challenge of driving here on Crete is you don't actually know when you're breaking the rules, because you don't get the feedback. You might be driving for 20 years, and a friend of mine was telling me his daughter's now done his driver's license, and next his wife is going to do it. I said, "What? Your wife doesn't have a driver's license?" No, and the next thing he's going to do is driver's license. And the guy's like 50 years old, doesn't have a driver's license, been driving since then, since he was a kid, because he's gotten away with it. And so this is a problem with concurrency, same problem. You don't get feedback when you make a mistake. And many years ago, we had this thing called swing, and we'd start writing swing code, and we'd end up with having lots and lots of really cool swing code. But what would happen is, as the programs got bigger, if we violated the rules, we'd end up with deadlocks, and these would then be very, very hard to find and to detect. So when I was working on my fourth teardown, I noticed this very weird comment, okay? And this is a comment. It says, static code block, and it says, prevent rare disastrous class loading and first call to lock support.park. And it points to a bug. And of course, I looked at that bug. And I did a little bit of digging in there. And it seems that in Java 7, class loading could, in very rare circumstances, consume the unpark. So there's a park that happens when your thread loads the class, but the class load itself might consume the unpark, which means your thread will never wake up again. And somebody at Google managed to discover this error, that sometimes they just have like a deadlock. The thread would just never get unparked. And he managed to write some test code to find this problem, but it had to run for like a week of CPU time in order to discover this problem. And he'd start and stop and start and stop until eventually he had the problem. So after a lot of backwards and forwards, they found this recommended workaround where they have the static initializer block, and inside there they simply ensure that the class is loaded, not initialized, but loaded. It has to be loaded, and that's it, then it works. But if it's not loaded, then you can end up with an unpark being lost or consumed by the class loader itself, and then the problem, and you end up with these problems. Now, in Java 9, the concurrent hash map loads lock support, and it's a different class loader. So I tried to figure out, is this still a problem? Because there are classes that use lock support which don't do this, but the only classes which have this, or which don't have the static code block, are new classes that are used since virtual threads. And so I asked the question, is this something which is still a problem? Yes or no? I didn't try to prove it, because if it took a really, really bright guy a week of CPU time, I do have other things to do in my life besides trying to find bugs. And so I didn't know. And in fact, no one could tell me whether this bug is still a problem or not, whether we still need this or not. And you'll see classes all over the place in the JDK which have the static initializer block, where they load the lock support class, and nobody really knows whether it's still necessary or not. So I don't know. And this is a problem. This is a problem with concurrencies. Sometimes you've got very hard to find bugs, very hard to reproduce bugs. Sometimes you end up with bugs caused by hardware. I was doing some consulting for one company, and I think the one problem they had was a hardware problem. They replaced some card, and it went away. But that's very rare. It's extremely rare when that happens. Most of the time, the bugs on our own code. So the reason why we should study java.util concurrent is because if we need to have any sort of state-dependent classes, it's best to use existing libraries, such as semaphores, blocking queues, count on latch, rather than trying to write our own. And so it's useful to study what's there, so that first of all we can learn what is available, and secondly we can figure out how to write thread-safe, robust classes by following the same techniques used within java.util concurrent. So that's the idea. So that's why we study this in great detail, so we know what to use. Now we have to know that everybody makes mistakes. In German we say, Vertrauen ist gut, Kontrolle ist besser. Basically, it's good to trust, but it's better to check up, because you never know if it's true or not. And so we're very used to using test-driven development, but this is super hard with multi-threaded code. Java concurrency stress tests can help, but it's still difficult to thoroughly test whether code is thread safe. And so it's better to rely on well-known synchronizers, not because the people who wrote it are cleverer than us, well, they probably are, but least clever than me, but because more people use their code. So if we write our own version of concurrent hash map, our very own one, there are chances that there's a higher chance that there's a bug in there than in concurrent hash map. And even within the JDK, it's better to use the classes which are most commonly used. So rather use concurrent hash map than concurrent skip list map, because it's more used. Rather use link blocking queue instead of link blocking deck, because that's more used. So we always take the ones which are most used, because hopefully the bugs have been ironed out and discovered. Anybody can report Java bugs, so you can do that yourself if you want to. And I've made a list of my own ones. I haven't done now for a few months, but I need to do that again. But most of the bugs in the concurrency are found in little used classes. So for example, link transfer queue I found in Java 1.8. Thread local random was a fun one. Concurrent skip list map, arrow blocking queue, and then 5 different ones in link blocking deck, and we fixed all of them in Java 26. And what we can see from this is that the less used a class is, the higher the chance of bugs. I've not found any bugs in the link blocking queue, or in the concurrent linked queue, or the concurrent hash map. There might be bugs, I haven't found them so far. And so, eat your own dog food. have a look at how many instances are used in the JDK. Concurrent hash is very widely used. The copy and write list is used a lot. The concurrent link queue and deco are used a lot. Future tasks and link blocking queue. And after that, we go into risky territory where they might be used, but they might not be used that much. And anything below this line here, we're looking towards maybe having errors inside. So we try to use the most commonly used thread-safe classes, and I've only found bugs in rarely used classes so far. Oh, yes, something. Before we continue, I've got a little gift for you. We're sort of 25 minutes in. It's a course I wrote a while ago, and it's a self-study course. So if you head over to tinyurl.com/ycrash25, you'll get this. Once you've got this course, you'll keep it for lifetime access. But I always say try and complete it before end of this year, so that you have a target by which time you must complete it. And you can ask questions in the course. All the comments are enabled, so you can ask questions in there. I was going to only make it available today, the coupon, but I'm going to make it until tomorrow, 10:30 Pacific time, to give people who are watching the recording tomorrow a chance to also grab this. All right. So make sure to get that, tinyurl.com/ycrash25. All right. So I want to look at another class which is quite interesting, which is striped64. And what we want to do is we want to compare incrementing a number 100 million times and compare what happens with atomic long versus long adder. So let's go first of all to our code here. This is going to be the striped64 demo. So I'm going to do atomic long, and we're going to make an in-stream parallel, and for each we're going to ignore the I, and we're going to simply say over here atomic long.increment and get. So let's just break this into a new line over there. All right, so this is the first approach, and we want to measure how long it takes to do this. So I've got a shortcut. Let me just do this again. This atomic time. Okay, there's a question by Pradeep Kumar. I'll see it just now. Hopefully they can pop that in there. And then what I'll do is I'm going to have another one, which actually is not part. How can we find these courses? Go to tinyurl.com/ the courses I've done, you'll see all my courses on javaspecialist.eu, the teardown courses. So the teardown courses are all on javaspecialist.eu. So they've got loads and loads of courses there, but they're not free. My children have to eat as well. And I do need money for speeding fines. Actually, no, I don't get speeding fines. It's not really possible to get speeding fines on Crete. Can't really drive fast enough for that. All right, so what I want to do is I want to just have one more class over here. It's going to be just a class, a synchronized counter. Nice counter. It's going to have a private long count, and it's going to have an increment count plus, and you see, now this is AI, right? It's written the code for me, and it's made a mistake. It's done increment synchronized and count not synchronized. So this is why this is one of the reasons why I went back to concurrency. Because when I end of 2023, I think it was 23 or so, 22, 23. I started getting bored, and I thought, let me go and do some AI stuff. And so I did this whole thing of translating a Cretan book from Cretan into English, and I used, of course, ChatGPT for that. But then I got bored of AI, and I thought, what can AI not do? And I thought, well, the one thing AI can't do is concurrency, because humans also can't get concurrency right. And there's a perfect example. AI is trying to do this for us, and it gets a very, very basic error wrong over here. So what I want to do is to also do the synchronized counters. We're going to make a var counter equals synchronized counter, and we're going to do an in stream over here, dot range dot parallel dot for each counter increment that is correct, and we'll wrap all of this into a synchronized time. Okay, so what I'll do is I'll just comment this out for now because I want to run the other one first. So we're going to run the atomic integer, atomic long, run that, and there's 2396. Okay, and you see it took like 2.4 seconds to run this. So my question is, for you is, if you think about it, how quick do you think it's going to be to do the synchronized one? So it took like between 2.4 to 3 seconds. The time's not going to be perfect because I'm also doing the webinar at the same time. But let's also do the synchronized version as well and see how quickly that runs. So the atomic time is like 2.5 to 3 seconds. And the synchronized time, whoa, 6.7 seconds. So in this case, the synchronized was actually quite a bit slower. Okay. Now, what I want to show you is something here. If we go to Java 17, for example, Java 17, I can't use underscore, so I'll have to say, just fix this quickly. I and I and I haven't done that one yet. So I'm going to run it in Java 17, Java source, main, Java, talks, teardown, demos. This is our Stripe 64 demo. We see that this is Java 17 now. The atomic time is 5 seconds, and the synchronized time is 3.8 seconds. All right? So this is how the time used to be in the past, 5 seconds, 3.8 seconds. But if you take Java 25, exact same code, atomic completes in 4 seconds, 1.7 seconds. Whoa, look at that. So it's all over the place. It's all over the place, this Java 26. But it's not fair because I'm actually running the webinar at the same time, so that's going to impact on my performance. But you see, in these examples, synchronized time is always faster than the atomic time. And atomic time seems to have improved since early versions of Java. All right. Now we'll try long adder. So we'll do in-stream, long adder increment, and we'll just put a timer around that. That's the long adder time. And we'll see how that performs. So the atomic time, 2.7 seconds, synchronized time seems to be slower. Really weird. I wonder if it's because I'm running it from inside IntelliJ. I've seen that before. This was Java 25, I think, is it? 3.4 seconds. 6.5. Okay, so it's all over the place. Java 26, let's do Java 25. It's as I said, it's very hard to run these tests with the webinar because normally I run it just with the projector with no screen recording and stuff like that going on. But you can see that the long adder time is like super fast. It's like 40 times faster than the atomic version. And even this one, even when it's fast, synchronous time, this is still a lot faster. So what's going on here? Is it magic? What's going on? So what we want to look at is to see how this Stripe 64 works and long adder. So long adder is a subclass long-adder is a subclass of a class called stripe64. Long-adder doesn't contain any code, any fields, but stripe64 does. So stripe64 contains a value. That's our base over here. And if we never have any contention on an atomic long, which is a stripe64, then we're simply going to update the base, and there won't be any further conflict going on. There won't be any conflict. It'll just be uncontended, updating the base and reading the base. However, if I've got two threads and they both try and update the base, and one of them loses the race to update, it's not a lock, it's using compare and swap, then what happens is what happens is that it's going to make a new array of these of the cells. It's going to make a new array of size 2, and allocate each thread to one of the cells. Hopefully, there'll be different cells, so the threads will look at different cells. If you get another conflict, it's going to double the number of cells again to 4, to 8, to 16, to 32, and it's not going to exceed the number of hardware threads you've got in the system, or rather, it'll go to the power of 2, which is closest to the number of hardware threads in your system. In my machine, I've got 12 cores. It's going to make up to size 16 array of cells. And the reason they do this is to limit the opportunity for having a clash on the cells. So if you have less clashing, you have less contention, less repeats, you get better throughput. And so basically what we're saying is that if we reduce contention, if we avoid contention, we get much better throughput. And that's what we're doing here with the striped 64. All right, so I'm going to take you back a few years when I started programming Java in 1987. And I really had to scratch my head on this one because 1997 is a long time ago. It's like 28 years ago when I started coding in Java. And at the time, I was working for a company, and we were doing, Java working on Windows NT, and we were using Java 1.1. We were, and the thing is that what we wanted to do is to we want to use Java like as our main language, but our machines were woefully underpowered. So, for example, my machine had 64 megabytes of RAM, a single core, 233 megahertz, and 32-bit. And this was one of the newer machines of the company. So that was quite something. The laptop I'm using now has 96 gigabytes of RAM, 12 cores, 38 GPU cores, 3.7 gigahertz, which I think goes higher if it's under pressure, and 64-bit. And as soon as this webinar is done, my son and I are going to run off to buy another computer for him. He's buying a laptop which is way more powerful than mine, except it doesn't have as much memory. So memory was very scarce, and at the time we couldn't imagine having a collection with billions of entries. And we also had platform threads, so we limited to thousands of threads rather than millions of threads. And what's interesting is quite often we'll find and bugs at the limits. So, for example, if you can have a lot of threads, a lot of memory, you're able to construct a link blocking deck with too many items. And I did this, for example, in my last newsletter, where I managed to create a link blocking deck with a negative value for size. And also there's a bug in reentrant read-write locks where you could run out of read locks after 65,000. So what they did is they took an int, they cut the int in half, so you have two shorts, and once we two shorts, but two 16-bit numbers, and once we exceeded 65,000, it threw an error. Because at the time when they wrote the code, they couldn't imagine a system with 65,000 threads. But we can imagine that when we work with virtual threads. So let's go quickly to another example. This is a many read locks. And what I'll do, I'm going to just copy and paste that. No, I can't paste it. Okay, never mind. I'll just explain it quickly. Basically, I've got a rent and read write lock over here. And I've got, and I'm making virtual threads up to 100,000 readers. And I'm going to submit until I get an error these jobs to the pool, and it's going to get a read lock, and then I'm going to simply wait until my count, which is the number of concurrent readers, has reached 100,000. So I'm going to keep on going until I reach 100,000, and then I exit from there. Now, if you run the code with Java 24, Java demos, this is the many read locks, Java 24, after not too long, we see max read is 65,000, and we get a Java lang error. So this is very serious. I didn't discover this one, unfortunately. Somebody else found it. And the fix is to simply change it to have two 32-bit numbers. So from Java 25, this is no longer an issue, and we can get up to 100,000. Now, I don't think you should, but you can. You can, right? Oops, that's the wrong button. Here's another one. Let's say you want to have a service that takes time to be started. So what I've done is I've defined an interface starting gun with the wait uninterruptedly and ready. And this is similar to the counter latch, but it's for only one item. But I don't want to worry about interrupted exceptions. Once all the data is set up, I'm going to call ready, and then all the waiting threads will wake up. So there are several ways of doing this. One way of doing that is to use the monitor locking. So you can make a Boolean ready equals false. We can have a wait uninterruptedly over here. With Boolean interrupted is threaded interrupted. And I'm simply going to say while not ready, we're going to wait. And if we get interrupted, I'm not going to exit. I'm simply going to note that I was interrupted, put that into the Boolean, and keep on waiting. So I keep on waiting until I'm ready. Once I'm done, I can say if I was interrupted, I re-interrupt myself, so exit in the interrupted status, and I'm done. And if I call ready, I'm simply going to say ready equals true, and notify all wake up all the threads which are waiting. Now this will sort of work for most versions of Java, but not for all, because wait notify is not compatible with older Loom versions. Now I saw in the chat there somebody asked the question about the Java versions. You should be on Java 25. I would say that major companies are probably, a lot of them are on Java 11, looking at Java 17, right? So that is quite common. That's quite common, unfortunately. But you should be on Java 25. That's really what you should be on. Because, ideally you should be on the latest long-term release, long-term stable version. So it's LTS, so that's your Java 25. But I know that a lot of companies are still on Java 11. But you really should push to go onto Java 25 to get all the latest features. All right. Because if you do this with Java 21, for example, you would end up with, and you've got a virtual thread, it's going to cause problems. So you could also do this. You could use a counter latch of 1 and simply delegate to that. You can delegate through to the counter latch implementation. And you start up, you get the interrupted status, you remember that, and then you, while true, latch it await. If it works, fantastic, you break out of there. But if you get interrupted, you're simply going to say you were interrupted, remember that, and then carry on waiting. And you keep on waiting until you have success. And And at the end of this, if you were interrupted, you interrupt yourself and you exit. Really simply latch.count on. Now, the nice thing with this is you don't have to worry about locking yourself. You're delegating to a well-known class. If there's a bug, then the authors of this class have to fix it. And the first example wasn't that great to do this because it's not fully compatible with virtual threads. Fixed in Java 24, but if you're in Java 21, you don't want to do that. Another way to do it, which you can try yourself as a demo, is to take count on latch and copy and paste that into your own class and use that. And if you ever look up a newsletter, I've got an example of that on the newsletter. Look for starting gun, you'll see it there as well. All right, now, there's an interesting class called link blocking queue. And link blocking queue has been designed to reduce contention between putting and taking. Now, it's not a brilliant design, but it's a general purpose queue. If you do have a use case, we've got a single producer and single consumer, there are better solutions using arrays, circular array structures, rather than linked structures, which have better performance. But as a general purpose queue, this is a good one to have. Now, what they did was they used two different locks, one for putting, one for taking, in order to allow you to put and take at exactly the same time. This has a higher throughput for the single producer, single consumer case, but if you've got multiple consumers, you can get some surprises. And the whole queue is interesting because they've got two locks and two different locks. So how do they make sure that the information is visible between the multiple threads when you've got two locks? And so what they do there is they've got as a referee between these two an atomic integer. Atomic integer has the count as a volatile, and that ensures that you get visibility between the multiple threads putting and taking from the queue. So it's really, really interesting. So I'm going to run the demo. I think this one will work. The other demo didn't really work the way I liked it, wanted it to work. But I think this one might work. So basically what I've got is I've got, first of all, one producer and one consumer. So it's a single producer, single consumer with the link blocking queue. And I'm putting a bunch of elements on there. It's going to be 10 million elements, and I'm taking them off again. So let's run that and see what comes out. So this is now the link blocking queue. You can see it takes about 1.1 seconds to run. I think this will work because I'm only using 2 cores. I've got 12 cores, so this one should work. So sort of the best time was like 970 milliseconds, so that's quite good. Now, let's try the same code with the link blocking deck. Now, the difference here is that you've got one lock for putting and taking, and so they're going to clash. So you're going to have more contention. And in this example, it's actually faster. These demos don't work because of the webinar. Unfortunately, there's too much going on my machine. And let me quickly do something. I don't know if this is going to work. I think this might work. Java. Just give me a second. I want to see if my this works. So I've got Java 25 on my. I've got like a demo server which I haven't updated recently. So this is silly. Okay, and let me quickly just grab this because I'm going to try and run this on my server. This is not the very latest version of the Where are we? Okay, this is the Git. Let me quickly grab that. Sorry for this slight detour, but okay, that's the teardown talk. And the branch Git is, not sure if the branch, I think the branch is talks. This is not a public repository, so you won't be able to get that from the repository. But you can see the code and the recording, and you can type it in yourself. It's the best way to learn anyway that way. So let's say git check out that. No, it's misspelled. All right. Okay, so let's go and do this. Java, let's make it a bit bigger. Lock splitting demo is the one we want to do. Where's my mouse? My mouse keeps on disappearing. There's my mouse. A bit smaller. Up there. Okay, so Java and lock. Okay, so this is Java 25. And it's now running. At the moment, it's using the linked blocking queue. Okay, this is my server, and it's getting like 1.9 seconds per data point. It's Intel based, and it's a bit older than, or it's not Intel. It's one of the other manufacturers, and let's change it to link blocking deck. And run it again and see if it's different. So it's about 2 seconds, roughly 2 seconds. This one's also much faster. So the demo is not working the way it's supposed to be working. It normally works on my machine, but this one also doesn't work the way it's supposed to work. So I'll just continue my machine. So let me run it again with the deck. Maybe this time it's giving better results. So it's like 600, 800 milliseconds. And the link blocking queue, if you run that, again, it's slower for some reason. So it's sort of hit and miss. Sometimes the demo works, sometimes it doesn't. If you take the arrow blocking queue, this also is quite slow. Now, what's interesting is what happens when you increase it to 2 consumers, right? For 2 consumers, so it's always been that in the past, all the demos I ran, the link blocking queue was slightly faster than the other 2 with 1 consumer. But what happens when you've got 2 consumers? Yeah, this also is not really the way it normally works. Let's do the link blocking deck with 2 consumers. And now that's quite a bit faster than the link blocking queue. Okay, and the arrow blocking queue is also again quite a bit faster than the link blocking queue. So the link blocking queue loses the race with 2 locks versus 1 lock. And the reason is that in many cases, what we're going to end up doing is we're going to end up creating contention on the putting, but on the taking, but not on the putting. So we can put elements very, very quickly, but we can't take them out as quickly. Let's make this 8 and see what happens now. 8 consumers and one putter. Okay, so that performance is about 400 milliseconds. And if you do this with the link blocking queue, yeah, it's about 600 milliseconds, so it's quite a bit worse. But it's not as illustrative as other demos. It's very hard to run this with all the other software running on here. So where do we see this? So what's interesting about this is that it's actually, you'll find this link blocking queue being used inside a fixed thread pool. So if you're using a fixed thread pool, it's actually going to be using internally a link blocking queue, and that means that the moment that you've got more than one thread, you actually have contention on the take. So you can put elements quicker into the queue on the fixed thread pool than you can take them out. And of course, if you can put them in quicker, you end up with a very long queue, which ends up slowing you down because you end up with memory pressure. Unfortunately, this doesn't run as well as I hoped. I could have made a recording, I guess, of that, but it wouldn't be as fun. So I apologize for that. Okay, weakly consistent iterator. There's array blocking queue. And what's interesting about this is that they've got a weakly consistent iteration, which would mean that if you change the queue whilst you're iterating, you might or might not see the changes. But what they want to do is they want to also avoid like very weird situations where with the array block, it's actually a circular array queue, so it wraps around, and they want to avoid the situation where you are sort of walking over your own tail. So what they do is once you go around the queue, past your own head, they want to completely invalidate the references where you no longer can iterate. So for example, I've got a queue over here, 10 elements, I put 5 elements in there, I make an iterator, I print out the first 3, I then add another 5, and what I will see is the remaining elements, 4, 5, 6, 7, 8, 9, 10. But if I removed, for example, a few elements and I added a whole bunch of elements, it would then throw away the iterator and invalidate it. But the question is, how does the collection know about its iterators? It keeps weak references pointing to all the iterators. So if you look, for example, at your array blocking queue, which is over here, let's just go to this one quickly. Array blocking queue over here, you'll see there's a weak reference. So each iterator is pointed to by a node, and that's actually a weak reference. And that's how they manage to have all these iterators in play. And not cause a memory leak. The memory leak is a problem, so that's how they avoid the memory leak. The last thing is with the copyright array list. So what they want to do is a sort of quite sophisticated double-check locking. In the remove, they first get the array, and then they search whether or not the array contains the element. And if it does contain the element, then they try and remove it again. So they do a second remove. The first remove, the first one search, is done without a lock. They do have some synchronization. So if you go to the copy and write array list, here you see, there is some synchronization because the get array is returning array which is volatile. So that is not synchronized, but it's synchronization. But then when you say remove, then they synchronize again. And they check, is the snapshot still equal to the array that we have had before? If so, we can just remove it. We're done. Otherwise, we need to search again to make sure if the element is actually in there. And this is quite fun because they've got this label here inside the if statement. So if snapshot and then find index over there. Now, when I saw this code, I thought, I'm sure I can do this better. you know. But there's a reason why they write code like this within the java.util concurrent, and that is that they try to minimize duplication of bytecode. And that's to help the hotspot profiler to do a better job of optimizing the code. So there's always method in their madness, and studying this in detail will help you to learn that better. So we're coming to the end. If you're not on my newsletter, make sure to join and say hello. I always, when people join, I always send a hello message. So do reply and get to know each other. You're welcome to send me a LinkedIn request as well. LinkedIn, I'm just Heinz Kabutz, HeinzKabutz. But you'll get a link. You'll get an email if you sign up to the newsletter. You get an email with my LinkedIn details. And if you haven't, and on my website, I've got lots of other things as well, goodies you can look at, hundreds of newsletters. And as far as I know, my newsletter is the longest running Java newsletter in the world. I started it on the 30th of November, 2000, year 2000. So coming up next month is going to be my 25-year anniversary of sending out the Java Specialists newsletter. And it's sort of, it's quite stable in the numbers. It doesn't really grow or shrink. It's like people come and go there. But it's a really great bunch of people on there. Some fantastic, fantastic engineers. So you'll be joining a very elite group of people. And I've got this, as I told you, I've got this gift of this Java, of this data structures course. If you get that QR code on your phone, you're sure to sign up for it. And once you've got that, you'll be able to watch that as long as you want to. It's got a nice quiz on there. So the quiz will be, you can use the quiz to practice for if you want to try out how well you know data structures. So, do we have any more questions? Yeah, there's lots of AI slop in the world nowadays. It's quite funny. And you saw, I mean, I did the demo, right? I was doing the demo and I was writing the synchronized class, synchronized counter, and something so basic it got wrong. So, yeah, I'm busy. You might see me in January, Pradeep, but not as a Java, not teaching Java. Something very different to Java. And I'm trying to get back into submitting Java courses, but maybe you should complain. You should complain to O'Reilly and say, we want Heinz back, we want Java back, we want to get rid of this AI slop and actually have something fun and interesting on there. Not just everything AI. You know what I mean? So please do complain and say we want to have Java and we want to have Heinz. And maybe they will listen to you. I didn't leave on deliberately. It's just that the business is now going everyone wants AI. I've been going to Java conferences recently. Again this year, I started again this year. Actually last year I started, but I've been going to quite a few. And some of them are just, every second talk is AI something, And you can go to like one or two of them, but after that it gets really boring. It's like, yeah. So yeah, I mean, I use AI, but the problem is when you're doing stuff like concurrency, writing concurrent code, AI is going to just give you the wrong answer almost every single time. And it certainly wouldn't have found the bugs that I found. So my suggestion for AI is the following. So AI is going to take a lot of our jobs away, especially if our jobs entail rinse and repeat. If you're doing something which is just the same thing over and over again, they're going to take away your jobs, very, very likely, But you could say, well, IDEs took away jobs years ago. If your job was writing getters and setters and equals and hashcode methods, that was your job. Well, that's been, those types of jobs have been gone for ages, right? and they're just being redone by automated code builders. So basically what you want to do is to look at things that you're really good at and that AI just isn't very good at. It could be optimizing database schemas, or it could be GC log analysis, but look for specific things and concentrate on that, so that you end up not becoming redundant. And keep away from rinse and repeat. Rinse and repeat. If you do anything rinse and repeat, that's dangerous. If you do something which you could just redo the same thing over and over again, those jobs are at most at risk. Any other questions? No? All right. In that case, thank you very much for joining.
No, someone just
there's a
posted
question.
Yeah.
Okay, pop it over and we'll check it out. You got to be fast here, otherwise you don't get your questions in. Okay. Did you meet issues with multi-threading? The threads are not scheduled properly in Java. Apps. This is all one question, okay. Okay, so if you make a thread dump and the thread is supposed to sleep for 200 milliseconds at a time, then it certainly could happen that every time you do a thread dump, it looks like it's still sleeping. Maybe it's sleeping again. Maybe it's in a loop. Most likely, my guess would be that your thread is in a loop, even if you don't realize it's in a loop. So yeah, this is not really working for me. So for this question number 4, this is the type of problem I help companies solve. So if this is something that's causing you problems, first of all, I would not run production on Windows. So I'm sorry to say, would not do that. I've done that, I wouldn't do that again. So this is your first, I think, issue, is running it on Windows. I know you might not have an option. You obviously don't have an option, otherwise you wouldn't be doing it. Okay, so another issue, waiting for intercritical section. Well, synchronized method, somebody else has the lock, right? Some other thread is holding the lock. There's got to be another thread holding the lock. But so what I can say is, I'm not sure how to pronounce the name, presumptuously. Contact me, send me an email, and we can have a look at this as a consulting project, because it sounds to me like you have you don't have the option. I know I know you don't have the option. I know you don't, otherwise you wouldn't. But this is something we can have a look at. But send me an email, heinz@javaspecialist.eu, because these things, we'll have to look at the thread dumps together and actually check it. Java 21, that's pretty good. So just to give you a tip on this, there are layers, right? The first layer is our own code. 99% of the time, that's where the bug is. So for example, you've got a loop. Instead of just having sleep once, you've got a loop running there. Number 2, next layer is the application server running on. There might be bugs there. There's a chance, non-zero chance, but there could be bugs there. But then the next level, which is extremely likely, is that the bug is extremely unlikely. Extremely unlikely is that the bug is in the JDK itself, in the JVM JDK. So at that level, there are bugs, but these bugs are usually very difficult to, or very rare, extremely rare. So, like the hotspot compiler, very, very rare. It can happen, but it's extremely rare. And then even less chance is on the operating system, and even less is on the hardware. So you've got always layers, always start at the top saying most likely the problem's here, and boom, most of the time you find the problem there. But this is something where normally what I do, the way I do it is I'd do a consulting session, spend maybe an hour looking at it together, and hopefully we'll find it in that time. We had one customer, they bought 10 hours of consulting, and I think in half an hour we knocked out two bugs. It's like boom, boom. It's like, oh, okay. That was quick. But it shouldn't happen that a thread sleeps and doesn't wake up. So my guess there would be it's a loop. It's looping, and you don't think it's looping, but it's actually looping. But every time you look at it, it's sleeping because it's still sleeping. That's my guess. But we'd have to check it.
I agree, right? Maybe at that point you're putting for 200 milliseconds sleep, but the thread is looping. So whenever you take
that's what I'm saying.
Yes, I totally agree with what you're saying. Maybe it's sleeping at the 200 milliseconds. It's sleeping at the 200 milliseconds, but actually it is looping. Maybe it's not looping immediately in that part of code. Maybe there's some other code which is calling it repeatedly. And all those other instructions are going through quickly. So in a thread dump, because maybe you're capturing with the interval, it's always getting as if it's appearing, it's in the sleeping, but it's executing the other lines of code, it's coming there. Yeah. So you have to look into who is invoking that method and who is all the invokers to see whether there's any loop is happening outside of that method. Okay.
Okay, so the good news is that with synchronized, it's actually easier to find problems than with reentrant blocks, because there are more tools for that.
Yeah. Okay.
Interesting. Okay.
Look, that's interesting. Okay.
Could there be an interrupted exception that bypasses your logging?
Yeah. We don't know. Yeah, I think the code has to be looked up to comment on that.
So all I want to say is that it's not impossible. It's not impossible that the thread is genuinely getting stuck, sleeping. Because when it comes to concurrency, I basically don't exclude any possibility. Another question. Is this with virtual threads or with platform threads? It's probably going to be platform. It must be platform threads, actually. It would be platform threads, if I answer my own question. Because the virtual threads wouldn't appear in the normal thread dump. So it wouldn't be there. Yeah, it would have to be platform threads.
Okay.
So if, as I said, presumably, sorry for mangling the name, I don't know, I'm going to be in Kharkov next week at JDD. I don't know if you're going to be at JDD next week. Your name sounds like you might be at JDD next week. If you're at JDD next week, pop it, show me your code, and we'll have a look at it together. Maybe we can figure it out. But I'm always happy to do some debugging with the customer on this stuff.
Okay.
Yeah. Hello. Do you hear me?
Yes.
Yes. Thank you for your for answering the question. Yes, I'm from Poland, as you guess, and I don't plan to be on the JDD, but maybe I will somehow get in contact with you. So yeah, but also If you mention about interruption, we also catch interruption exception, and it's a very strange situation, unfortunately, on Windows.
It's
So I also wonder if you have any experience with Java on Windows. This is actually a desktop application
okay.
with many threads. But yeah, it's quite complicated application. So, and I don't know any other, let's say, maybe I know only IntelliJ and Eclipse, which are running on Windows. So I was also wondering whether there are lots of applications of Java on Windows.
Not. I mean, yeah, not that many. I mean, they do use them, but yeah, it's been many years since I used Windows at all.
Okay.
And Java on Windows is, I used to program Java on Windows in 1997, right? But since about 2002 or 3, I've not done any more Java on Windows. What I'm saying is that it's not impossible. It's not impossible that Windows has a bug, that the Windows version of Java has a bug, and I'll look into it. I'll see if I can find anything. But I sort of doubt it, but it's not impossible. It's sort of very unlikely, but it's not possible. Which Windows version are you using?
10 and 11.
And it happens on both.
I think yes. I'm not sure now, but maybe. And furthermore, this application runs on virtual machines, so under hypervisors.
So can you do are you able to write a small piece of code that does the sleeping which gets stuck?
Okay.
Because if you have like one example that says, look, this thread is on a hypervisor, it gets stuck after 2 days, whatever. You could maybe start 1,000 threads. It could start 5,000 threads, make them all sleep for 200 milliseconds and do stuff, and see if any one of them gets stuck. If any one of them doesn't respond within a second or 2 seconds, you raise the alarm that this one got stuck. And that way you can actually
mean to try to repeat in a minimal example, let's say this
yeah, absolutely.
Maybe then try to let's say make a ticket on JDK bug.
Yeah, exactly.
Okay.
That's absolutely right. That's what I would do.
Okay, thank you.
Wait, Rico has an idea. It's not impossible. Windows, this can happen, but you would have to have a high priority thread. The scheduling isn't that great on Windows, and certainly if you have high priority threads, you can get starvation. What Rico's saying is maybe you've got getting starvation, but I can't imagine that. Not in Windows 10 and 11.
So Premsila, does it happen always? That the sleep problem, does it happen always, or it happens occasionally, or what is the frequency? Okay.
Oh.
Okay. So looks like Premsla is not able to answer. Okay. So any other questions? If not, we can wrap up the webinar. Okay, we'll wrap it up. So Ames, thank you very much for this such an interactive, wonderful session. We learned a lot. It's very helpful.
Thank you very much.
Thank you for taking your valuable time. Okay, truly appreciate it.
Thank you. It's been fun.
Yes. Okay. Bye.
See you around.
Yes.
Bye-bye.